This is the lecture over Chapter 8 of your textbook entitled Advanced Data Handling Concepts. In this chapter, we're going to learn a few things. We're going to learn about what sorting is. In particular, we will use the bubble sort algorithm because it's fairly straightforward to understand, not the most efficient, but easy to understand. We'll talk about what records are and what multi-field records are. We'll talk about a sort called the insertion sort, which is another algorithm. Again, relatively easy to understand, but maybe not the most efficient to use in real life. We'll talk about what we mean by multidimensional arrays, and then we'll talk about indexed files, and we'll talk about linked list. So, first of all, let's talk about sorting data. Sorting data is putting data in order by some particular rule or set of rules. The most common and easiest to understand, because we do this occasionally, is to sort something alphabetically. So a lot of times we'll see a list that's sorted alphabetically by last name, for example, or to sort things numerically. I know a lot of times I deal with how much disk space people are using, and I would like to sort it from the person that is using the most disk space down to the person that is using the least. The first example I gave, where we sort by last name, A to Z, or lowest to highest, that's referred to as ascending order. If we sort something from highest to lowest, in the case of alphabetical, that would be Z down to A. Or in the example I gave where we were looking at disk space and I wanted to see the person using the most disk space at the top, that would be referred to as sorting the items in descending order. So when comparisons are made, these are typically made by numeric value. If we're sorting numbers, that kind of makes sense. We sort numbers, we sort them by numeric value. But letters are represented in a code, most often ASCII, which stands for American Standard Code for Information Interchange. The numeric value for B is, or if you take the encoding of B in memory and you think of it as a number, it is going to be numerically one more than the ASCII encoding for the letter A. So the comparison happens always based on numbers, but if we're sorting something where each byte represents a character, then that comes out in alphabetical order for us automatically. This is talking about writing sorting algorithms or sorting programs. A lot of times you might want to do that, especially if you have some what might be considered unusual or uncommon way to sort the data. But if you're sorting things numerically, alphabetically, etc., you can actually purchase programs that do this sorting for you. I'm familiar with one that we used to use on our IBM mainframe computer called SyncSort. Now, these sort programs that you buy, maybe anywhere from relatively inexpensive to, thousands of dollars a year. Obviously, in most cases, the more expensive products are going to give you more functionality and or perform the sort more efficiently or more quickly. Regardless of how you're going to do this, in computer science and in programming, it is beneficial for you to understand the sorting process. So what we're going to do is we're going to start with something called the bubble sort. So we have an array of, let's say, numeric values, and we would like to sort them so that the 0th position of the array had the smallest value and the last element of the array had the largest value. So we would be sorting them in ascending order. Basically what bubble swap does is it goes through the array looking at two adjacent locations, and if the second location happens to be less than the first location, it performs a swap. and then it'll move down and look at the next pair. So when we go through, we're swapping values that are not in order. We'll see kind of a way to shortcut this. One way to do this is say we just keep going through the array over and over and over, each time or each pass through the array, counting how many times we swap values. And whenever we look at that and we say we swapped 0 values, that would be our indicator that the array was properly sorted, and we could stop that process and continue on with whatever our program was supposed to do next. This sometimes is called a sinking sort. Basically, it's a sinking sort because after the first pass through, the largest value will sink down or get swapped down to the very bottom. The name bubble sort comes from the fact that values bubble up so that the smallest values come to the top. So it's kind of two different ways to look at that. I think we've seen the term algorithm before, but an algorithm describes how to do something. In this case, I mentioned swapping values, which I don't think we've talked about before. So if we had two values, X and Y, and we wanted to trade them. They say there's a trick to swapping these. I don't know if I'd really call it a trick, but there's something you need to be aware of. If you do this incorrectly, your program won't function correctly because you lose data. So basically here we have two numbers, score 1 and score 2, and we would like to change the values. Well, what happens is if we say, okay, I'm going to set score 2 to whatever's in score 1, and then presumably turn around and set score 1 to whatever's in score 2, after we execute the set score 2 equals to score 1, both of the values now have a score of 90, and the value 85 was lost. So the way we do this is we have to have a temporary value. So what we do is we set aside the value in score 2 in this temporary variable at the bottom of the page. Then we take the score that's in score 1, place it in score 2, and then in score 1 we place the temporary value that we've been holding. And at that point we have traded the score values. Kind of a funny story I have from like decades ago. I used to teach CS250 at UK, and I had another instructor that was dealing with a student, and they just could not understand why you need a temporary value. And she was getting very, very, very frustrated. So what she did was she grabbed a couple items off her desk, and she put one of those little plastic tape dispensers and one of the real cheap plastic ones, and then she put a really heavy stapler. And it's like, okay, if I want to switch these two items, what do I do? And the person said, well, you move the stapler to where the tape dispenser was. So again, I said she was really, really frustrated. So she picked up this big stapler and just smashed the tape dispenser, and it shattered it. Pieces flew everywhere. And then the student said, oh, I guess we should have moved the tape dispenser first. And then at that point, the student understood why there was a need to place one of these items in a temporary location so that it would not be destroyed. Obviously, in programming, we're talking about logically destroyed. In her example, in the story I just told you, we're talking about physically destroyed because you did not move it. So this is just a little flow chart and pseudocode that basically matches up with the process that we just went through and discussed. So now what we're doing is we're switching gears now that we know how to swap something and talking about the actual bubble sort. So here on slide 10, we declare some variables. Some of them are static constants. What we do then is we're going to look at three methods or three functions. One called filled array that's going to get the values, the scores into the array. Then we're going to go through the sort array, which is going to implement the bubble sort. And then we're going to go to display array, which will show us that yes, indeed, our sort algorithm did work correctly. So in fill array, this is pretty standard. While there's more room in the array, we want to ask for a score, read that from the user, and then increment our index or counter, depending on how you want to look at it, to be the next position of the array. Once we fall out of that, in particular, x gets to be set to size, that decision is going to be true. We're going to fall out of the loop, and then we're going to return the flow of control in the program back to the main program. Now then, here they have what I would call a first pass at the bubble sort. So the heart of this is kind of in the middle towards the bottom, where you have x set to an index, and you're saying while the xth index into our score array is greater than the x plus 1 location, we need to swap those. So they're kind of delaying the logic using good coding here and just saying swap these two values and continue on. Now, the problem with this is if you look at this and kind of trace through it, I think you'll see that we're only going to make one pass in the array. So what that'll do is that'll get the largest number to the bottom, but then it won't go back and deal with any of the other values that might be out of order. We'll address that in a moment, but right now we kind of hid the algorithm or the logic of the swap function. So what the swap function does is it takes our x plus 1 position of our array, stores it in temp, it moves the x location down to the x plus 1 location, and then it takes the temporary value and stores it in the x location of the array. So there's pseudocode for that, and then there's also the matching flowchart. So what that'll do is that'll swap two values, first value at location x, the second at location or index x plus 1. Now then, on the next 2 or 3 slides, they're going to show you what's going to happen or what we need to happen. So what happens is we make an initial list that is shown on the top left. So we look at the first two elements, 0 and 1. They are not in ascending order, so we need to switch them. So you'll see in the top right those are switched. Now, if we advance down to a counter of 1 and we look at location 1 and 2, they're in the correct order, so we don't need to make any change. Now, if we go down and look at this on the next pass, the 75 and the 95 are going to be switched. So what we've done is that 90 has migrated to be the last element of the array. Now then, we go back to the top, set x to 0, and we look at these. So 65 is less than 85, so we don't need to make a change. If we move x to 1, we look at the 90 and the 75. Well, those are in the correct order. So, I'm sorry, they're not in the correct order, so we'll swap those two. And that 85 bubbles down. So you'll see that at the very end, if we go through this array over and over again, switching the values, anytime we find a value that is greater than the value below it or with the next highest index, depending on how you want to look at it, that we will end up with an assorted array. Now then, what they've done here is, since we need to keep going over this, what they're going to do is they're going to put another loop variable that goes through and does a number of comparisons for us to make sure that we pass through the entire array. So that being the case, we've put a loop within a loop. Doing so is called a nested loop. I think we learned that a few chapters ago. The inner loop is the one that swaps out of order pairs, and then the outer loop, in this case, the one whose index variable is being incremented less frequently, makes sure we go through the list multiple times. If our list is totally unordered, the greatest number of times that we will need to pass through the array is one less than the number of the arrays. So if we have a 20 element array that's in totally reverse order, we will need to pass through it 19 times. Now then, we will also need to go through, potentially, through the list, the number of the arrays. So I think I said 20 element array, so we would need to do that 20 times. So as you might imagine, especially in the example I just gave, going through the bubble sort, you can do that many times. Now then, in the example they gave, we had a fixed number of values. In the case of sorting a list, you might tell the user, hey, you can sort a list as long as it does not have more than 100 elements. So what would happen is if they gave you a list that had 22 elements, a lot of times what you do is you might have a variable, for example, called number of, in this case they say L's, which is an abbreviation for number of elements, and store the 22 in that. And then the number of comparisons you're going to need to do is that number minus 1. The reason being is because we always look at, in the previous algorithm, x and x plus 1. So number of elements minus 1, we would compare it to number of elements minus 1 plus 1, which would be the number of elements. So there's one less we have to do because we're comparing two items from the array. So what they've done here is they've gone back and taken the flowchart, the logic of the bubble sort, and gone through and added the fact that we may not know how many elements we're going to get from the user when fill array is called. Okay, so if we're doing an ascending sort, we've already mentioned this. After the first pass, the largest value is guaranteed to be in its correct final position at the end of the list in the array. If you're doing this in descending order, then you're guaranteed to have the smallest element in the last element of the array. So the next time we go through, we're guaranteed to have two items in the correct place. On the third pass through, we're guaranteed to have the last three. Now then, since we know that fact, let's say we have a 100 element array. We've gone through it 50 times. Therefore, we know the last 50 elements are in the correct location. So there is no need on the 53rd pass to go through and look at those 50 items that we already know are in the correct location. So what we can do is we can use that fact to make our program more efficient. That is, don't have it doing a whole bunch of comparisons that it doesn't need to do because we already know they're in correct order. So what they're going to do is create a new variable called pairs to compare. The first time it will be set to number of elements minus 1. We discussed about why that minus 1 was there before. But so the first pass through for a 20 element array, we would do 19 compares. After we made that pass and know that the last value is correct or in its correct location, we would decrement pairs to compare by 1 down to 18. So the last element that we would look at would be 18 plus 1, or the 19th element. After we get the 19th element correct, then that would go down to 18, etc. So this allows us to very efficiently go through and our algorithm and get our list sorted, but not wasting computing resources or computing time. So what they've done here in the highlighted place in the pseudocode and the flowchart is they've added that pairs to compare, and then they show you where to check that to see if you're done and where to decrement it by 1 on each pass through the array. Another thing you can do is you can actually, as I mentioned before, you can count how many swaps you made. So if the list is already semi-sorted and you have a 20-element array, it could be possible that on the 5th pass through the array, the list is already in sorted order. So what you can do is you can either count, which is what I said, or in this case they're using a Boolean value that we've discussed before that is a true, false, or yes, no value. And they'll set did swap to no. They'll set it to yes. And then if they go all the way through and don't swap anything, when you come out of the loop and go back to the top, it'll ask the question, is did swap still set to yes? If the answer is no, then you can terminate your loop early. So that allows you to save, again, some computing time once you know the list is already in order. Another thing you might have to deal with is when we deal with the concept of parallel arrays, we talked about how the nth position in the first array has data related to the nth position in the second array. So here it looks like we have the first name of some students and their associated score. So Brad is in location 2 of the first array. So location 2 of the second array has the score of 60. So that means Brad made a 60 on the exam. If we wanted to sort this, I'm not sure. I'm going to peek ahead here. If they're going to sort alphabetically by first name, anytime we make a swap or a move in the name array, we need to make the exact same change in the score array. Now then, if they're doing the difference, which is sort from high test score to low test score, for example, in descending order in the score array, anytime we make a change to the score array, we need to make the exact same change to the name array so that the person's name stays with their grade. So those are the two possibilities if we have two parallel arrays. So what they're doing here is a couple ways to do this. We could create something called a record or a class. Different languages use different terminology, but basically, we can say, hey, we have a student record. That student record has a name and score, and then that way the name and the score are always together. But we're not going to talk about this for a couple of more chapters. We'll start in chapter 10 and talk a little bit more about it in chapter 11. And we would define a class, which is a method that would allow us to sort by whatever we want to. So what they're showing here is an insertion sort, and then what happens is the value is inserted to the correct location. So basically, if we wanted these in ascending order by numeric value, and we start with our original array, basically we would go through the whole array, very similar to what you did in a programming assignment, and say, what is the smallest value I have? And then once you know the smallest value is 65, you would, again, using a temporary variable, put that in its correct location. We would insert it into its correct location at position 0, and we'd just move the 90 down to where that 65 was, in this case in location 2. So that's why that is called an insertion sort. We would then go to location 1 of the array, and from location 1 to the end of the array, find the smallest value, and in this case it's 75. So we would insert that at location or index 1 of our array. And we would do that 2 more times, because again, if all the items are in the correct order except the last one, then the list is in the correct order. So here we have a flow chart that goes through, and implements the insertion sort. So we're going through and just moving the values around. So you can look through that. What we've been talking about to this point when we talk about arrays is one-dimensional arrays or an array that has a single dimension. Either of those are fine. Another term that would be used is a list. Now, I don't really like the middle point here. They say data can be stored in a table that has just one dimension, height. They're really, if you have one-dimensional array, you talk about a list, and that list has multiple locations. I don't really like them using the term table because, as you'll see now, a two-dimensional array has height and width, rows and columns, and we refer to a two-dimensional array as a table. So basically, you can think of this as like a set of mailboxes where you have mailboxes across, you have mailboxes up and down, and you need to say, okay, go 3 rows down from the top, 4 boxes to the right, and that's the location I want to examine. So what they use in the textbook is an example of apartment building. So this apartment building they're talking about has 5 floors. Each floor has either a studio or has some number of studio, 1 and 2 bedroom departments. And to determine the rent, you need to know what floor they're on and the number of bedrooms in the apartment. So obviously, you know, a 2-bedroom apartment is going to be more expensive than a 1-bedroom apartment, which is normally going to be more expensive than a studio. The price may vary by floor because if this is a walk-up, you know, in New York City, for example, that doesn't have an elevator, rooms on the 1st and 2nd floor are going to probably be more expensive than those on the 3rd, 4th, and 5th because you're going to have less steps that you have to deal with. So here is what they did. You know, there are 5 floors, so we have an item. Notice that we're thinking about programming this, so the ground floor would be floor 0, so that it matches up nicely with our arrays where indexes start at 0. And then it's going to work out nicely as far as the columns because the studio apartments can be column 0, 1-bedroom apartment can be column 1, and a 2-bedroom apartment can be column 2. So I guess they took a little different logic than I did. It looks like they're considering apartments that are on the higher floors to be more expensive. You know, that might be the case, in my opinion, of a penthouse, but not a 5-story apartment building. But anyway, that's how they set that up. So when we have a two-dimensional array, we have to declare the array to have 2 dimensions, which they've done right there in the middle. It has 5 rows and 3 columns. And just like a one-dimensional array, the row goes from 0 to 1 less than the maximum dimension. So in the case of this one, it goes to 0 to 4. And the columns go from 0, 1 less than the number of columns defined. So here they're trying to show you what this array might look like as well, with the indices placed there and the declaration. So the name of the array is rent by floor and bedrooms. So as we saw, if we have 2 dimensions, we need 2 square brackets or parentheses depending upon the programming language. But here in this pseudocode, they're showing you square brackets. To access a 2-dimensional array, you give the row and column number in square brackets, and it will go to that row and column in the array and pull the value out. Now, one thing that's important is, you know, this may look very different than, for example, having a variable called cost or rent. But anywhere a simple variable can be used, we can use a value that is retrieved from a multidimensional array, in this case a two-dimensional array. Here is the flowchart and the pseudocode. Notice how they are declaring the two-dimensional array in the declaration section of both the flowchart and in the pseudocode. So basically what they do is they ask the person, how many bedrooms do you want? What floor do you want to be on? And then it will go pull the value out and tell the user of the program what their rent would be if they chose that apartment. So you can extend multidimensional arrays. Some languages it's relatively low, in other languages it's crazy big. But three-dimensional and higher arrays are supported by many programming languages. Even the implementation of BASIC that we're using in class supports multi-dimensional arrays. It may have a limit of 4 or 5, but that solves most problems. So in this case, they are still using the concept of you're renting apartments out, and we already have what floor you're in, what bedroom you're in. Now we actually add a third dimension, which is building. So to specify or to get the rent, we need to know what building you're in, how many bedrooms you want, and what floor you want to be on. So you need to keep these in order. Here they've declared floor, bedrooms, building. So anytime we reference this, we would need to give values that correspond to the appropriate thing. For example, the first value will always be what floor you're on. The last value will always be what building you're in. Another example I want to mention is we live in a three-dimensional world. So a lot of times we use three-dimensional arrays to represent data like a building or an object, a sphere, a cylinder. Those are things that are three-dimensional in nature, so we could use a three-dimensional array to define those. So I just wanted to give you another example of using a three-dimensional array. So in this case, we still have rows that represents floors and columns that represent bedrooms, but you can kind of think of what building they're in as a z-axis, kind of coming out at you. So you would choose the correct row and column two-dimensional array that corresponds to the building we're in, and then once you get that right sheet or set of numbers, then you would use the row and the floor the floor and the number of bedrooms to get the price. Another thing that we deal with often in computing is referred to as indexed files. That is typically a file that has lots of numeric values. For example, at UK, we have tens of thousands of employees, so maybe this was keeping addresses and pay rates, etc. And they, want to keep this in order by some value, maybe employee number, or maybe they want to do it from highest salary down to lowest salary. It's going to take a lot. We would not want to use a bubble sort to go through and do this. It would be very, very slow. But two things that we need to understand related to index files are we have a physical order, which is how they exist on physical storage, such as a hard drive. And then the logical order is some order that we might place this in based on criteria we choose. Now, a lot of times when we sort things, we change the logical order, but we do not actually rearrange the data on the hard drive. That would be very inefficient and very time-consuming. So we just come up with this concept of index files. And what happens is we have a key for each field, and then what happens is we keep that key in the correct order and have it point to the actual location on the physical storage. So physical storage might be a hard drive, it might be memory. Let's think about memory now, but the concept is the same. Each memory location on a computer has an address. And what happens is if we say go to location 40,000 on the hard drive, it will retrieve to us whatever is in the 40,000th location on the drive. Now what happens is the index record is used to store that address to go out and get the actual data. For this to work, the records have to be stored on random access storage. Hard drive is random access. Memory, RAM is random access. That's what the R and the A is in RAM. Flash drives, flash memory is random access. The one thing that I can think of right offhand that we've talked about that is not random access is the fact that we have magnetic tape, which is usually sequential access. We have to look at all the data up to the point we find the information that we're looking for. One way they're drawing an analogy is an index in the back of the book. If you want to find some particular information and you can't remember where it is in the book, you will often go to the index, look up the word, and it'll say, oh, that's on page 82. So we can do the same thing with whatever ID numbers or memory addresses that we are using. When a record is removed from an index file, you don't have to actually physically remove it. You just remove the reference in the index file, and it will appear that that data is there. So maybe you want to have a view of this file that has the current employees, but just because somebody quit, you don't want to delete all the information you have about them. So in this view of current employees, you would just remove the index that pointed to people who no longer worked at your organization. So here they're showing you a hard drive. We have an index location. We sorted this by ID. So if we're looking for the person with ID 222, it would say, okay, you need to go to location 480 on the disk, and then whatever is in location 480 shown kind of at the bottom left here in the diagram, that would have the information for the person who had ID 222, for example. Another way to order data is through something called a linked list. A linked list, you have a start of the linked list, which points to a memory location or a chunk of data in memory, and that contains all the information about the first person in the list. That first item is going to have a link to the second item in the list. And if we follow that link to whatever location on the hard drive, we would find information about the second item and there being a pointer to the next record. Whenever we get to the end of the list and there are no more records, they may mention this here in a moment, but we put something called the null pointer. That is, there is no other pointer that we need to deal with. If you need to add a new record, you search through the list, find the correct location for it, you take that pointer to point to the new record, and that new record has a pointer that points to what now becomes the next record in the array. We will need a temporary variable, just like swapping things, to go through and do that to hold the pointer to the rest of the list while we insert the new item into the linked list. Here we have an example. Usually you draw this as a bunch of boxes that have errors between them, but they're trying to stress that, okay, the first item in the linked list at location 0, ID 111 belongs to Baker, and here's their phone number. Now, if we want to go to the next customer, we need to go to address 7200. Address 7200 on the disk has employee ID or ID number 222. The name is Vincent. There's their phone number. The next record is 4400. If we follow this to the end, notice that the last line at address 6000, the next customer record address is EOF. So they're using EOF here. Most programming languages would use null. But either of those are acceptable. People are going to know what you're talking about if you use either of those terms. Now then, if we want to delete something through a linked list, we would search through the list, find the item that needs to be deleted. We would then take the item to be deleted, we would get its next record pointer, and we would store it in the item before it. So we would link past that item, and it would no longer be part of the linked list. Again, we don't actually have to delete this from the storage unless it makes sense to do so. Down at the bottom, they call this a more sophisticated linked list. It has the address of the next record in the list as well as the one before it. This is normally referred to as a doubly linked list. It's linked in two different directions. So that finishes up Chapter 8 of your textbook, and it's just showing here in the summary some of the things that you would have learned.